we're going to be looking at transformers. A transformer makes use of electromagnetic induction to increase or decrease alternating voltage. And it has three main components. It's got a primary coil, which is our input, the secondary coil, which is our output, and an iron core that links the primary and secondary coils. Alternating current through the primary coil creates changing magnetic field or changing magnetic flux, which then links to the secondary coil. So the changing magnetic flux linkage in the secondary coil induces an EMF. This induced EMF is our output voltage from the secondary coil. The function of the iron core is to link all the magnetic flux from the primary coil to the secondary coil. And so these lines are representing the magnetic field lines. For a step-up transformer, you have more number of turns in the secondary coil than you have in the primary coil. And so that's symbolised by NS is the number of turns in the secondary, and MP is the number of turns for the primary. As you have the same amount of flux from the primary linking to the secondary coil, then the magnetic flux linkage in the secondary coil, which is equal to the number of turns multiplied by the magnetic flux, is going to be greater in the secondary because it has a larger number of turns. The induced EMF across the secondary coil will equal to its rate of change of magnetic flux linkage, and as it has a larger flux linkage, then the rate of change of flux linkage will be greater, and so the EMF induced will be greater, and so the voltage across the secondary coil will be greater than the input voltage that was across the primary coil. So we've stepped up the voltage. For a transformer, the ratio of the number of turns is equal to the ratio of the voltage, and this can be expressed as an equation where number of turns in the secondary coil divided by the number of turns in the primary coil is equal to the voltage across the secondary coil divided by the voltage across the primary coil. So if the number of turns in the secondary coil is twice that in the primary coil, so that will give us a ratio of 2 to 1, then the voltage ratio will ought to be 2 to 1. So that is, the voltage across the secondary coil will be twice that across the primary coil. For an ideal transformer, its efficiency would be 100%. So we can say then that the total input power will equal the total output power. And so power is found by current multiplied by voltage. So the current times voltage for the primary coil will equal the current times voltage for the secondary coil. This being the input power and this is the output power. So for 100% efficiency, if the voltage is stepped up by a certain ratio, then the current must step down by that same ratio to keep the total power the same. And we can see this is so by substituting the turns ratio equation into this efficiency equation, eliminating the voltage, we get this. And if we rearrange to get the turns ratio, you can then see that if we step up the number of turns, then the current will step down by that same ratio. However, the transformer efficiency is around 95 to 99%, and so the efficiency would be calculated from the output power, which is across the secondary coil, divided by the input power, which is across the primary coil. And if we substitute the turns ratio equation into our efficiency equation, eliminating the voltages, we get this. And it's important to note, because the transformer is not 100% efficient, this equation is no longer true. So the current will not step down by the same ratio as the voltage steps up, or the turns ratio steps up. So have you ever wondered why mains voltage supply is alternating and not direct? Well, it's all about transformers. So you've got the power lines carrying the power from the power station to the main supply, the homes, schools, colleges, buildings. And so because the power lines have resistance, you're going to get power losses, I squared R power losses along the power lines. And so in order to minimize this power loss, we need to reduce the current that is going through the cables. So in order to do that, we would need to increase the voltage across the cables to transmit the same amount of power. So to increase the voltage, we would need a step-up transformer. This transformer will step up the voltage to around about 400,000 volts. And so a step-down transformer would be needed to reduce this voltage to around 230 volts, the main supply. So we need the transformers to step up the voltage in order to reduce power losses along the power lines, and transformers only work using alternating current. The alternating current, remember, provides the alternating magnetic flux linkage that induces the EMF across the secondary coil.